Hi everyone! In this presentation, we'll explore one of the most fascinating advancements in modern technology, quantum computing. We'll uncover what makes it different from the computers we use today, how it actually works at a conceptual level, and what breakthroughs are happening right now that could redefine the future of computation. By the end, you'll have a clear, intuitive sense of why the world's biggest tech and research institutions are aiming to master this technology. Here's how we'll break things down. We'll begin with what and why, the motivation and promise behind quantum computing. Then we'll move into the core concepts superposition, entanglement, and interference, which are the heart of quantum revolution. Finally, we'll wrap up with hardware and outlook, looking at how these machines are physically built, the obstacles researchers are tackling, and what the next decade might hold. Let's start with the basics. Quantum computing is a new approach to processing information that draws directly from the rules of quantum mechanics, the branch of physics that governs atoms and subatomic particles. In classical computing, information is stored in bits, each representing either a 0 or a 1. But in quantum computing, the smallest unit of data is a qubit, a quantum bit, that can exist as a 0, 1, or both at the same time. This behavior, called superposition, gives quantum computers a fundamentally different kind of computational power, one based on probabilities and parallelism, rather than strict binary logic. The limitations of classical computing become clear when dealing with massive complex problems. For example, factoring very large numbers, which is something critical to modern cryptography, can take even the fastest classical computers thousands of years. Quantum computers, by exploiting superposition and entanglement, can process many possibilities simultaneously. This gives them exponential advantages for specific problems like simulating molecules, optimizing traffic networks, or even breaking certain encryption systems, which are tasks that will overwhelm any conventional machine. So, what exactly is a qubit? A qubit is a quantum version of a bit, the fundamental building block of quantum information. While a bit can either be 0 or 1, a qubit can be in a superposition of both states at once. You can imagine it like a spinning coin because while it's in the air, it's both heads and tails, only collapsing into one outcome when it lands. Physically, qubits can be represented in several ways: the spin of an electron, the polarization of a photon, or even tiny electrical currents in superconducting loops. These qubits are controlled and combined through quantum gates, which manipulate their states and allow us to build quantum algorithms. Superposition is what allows quantum computers to explore multiple solutions at the same time. For example, imagine trying to find the shortest path across 100 cities. A classical computer would check each route one by one, a nearly impossible task as the combinations explode exponentially. A quantum computer, however, can evaluate all possible routes simultaneously in superposition, giving it a massive head start over finding the optimal solution. This is why many researchers believe quantum computing could reshape fields from logistics and finance to artificial intelligence. Entanglement is another cornerstone of quantum mechanics and perhaps the most mind bending concept. When two qubits become entangled, the state of one instantly influences the other, no matter how apart they are. In computing, this means qubits don't act independently. They share information in a deeply connected way, allowing for incredible computational parallelism. Entanglement enables quantum computers to perform complex operations over many qubits in a coordinated fashion, which classical bits could never achieve. Now, how do quantum computers actually find the right answer among so many probabilities? The key is quantum interference. Just like waves of light can overlap, sometimes amplifying each other and sometimes canceling out, quantum algorithms use interference to strengthen the probability of correct answers while suppressing the wrong ones. After interference, we measure the qubits, forcing them to collapse from superposition into definite zeros and ones. The pattern of those measurements represents the solution to the problem we asked the computer to solve. So far, we've been talking about theory, but what do real quantum computers look like? Modern quantum machines are built on several competing hardware platforms. The main approaches include superconducting circuits, trapped ions, and photonic chips. Each method has its own trade offs between coherence time, control precision, and scalability. Many major challenges remain. Decoherence is the tendency of qubits to lose their fragile quantum state when interacting with the environment, which give limits to how long computations can last. Error rates are still far too high for large-scale algorithms, and scalability, which is adding more qubits without introducing more noise, is an enormous engineering task. Researchers are also developing quantum error correction codes to detect and fix mistakes without destroying the quantum information itself. Despite these issues, progress is still accelerating. In the near term, quantum computers will assist in simulating new materials, designing drugs, improving financial modeling, and solving optimization problems that classical computers can't officially handle. As quantum hardware matures, we'll see hybrid systems where classical and quantum processors work together. If you'd like to explore more, platforms like IBM Quantum Experience or Qiskit Playground can let you write and test your own quantum programs online. Thank you for watching and welcome to the quantum era.